Welcome to Sleepy Universe. When you hear about space travel, what comes to mind first? Do you imagine the moment Earth slowly shrinking behind you? A black sky opening wide, filled with thousands of stars, and a feeling of excitement, like leaving home to visit a place you expect to be breathtakingly beautiful? The reality of leaving Earth is far quieter and far harsher. The moment you step beyond this planet's atmosphere, the invisible protections your body has always relied on begin to disappear. There is no natural air pressure holding your body together, no oxygen waiting to be breathed, no clear sense of up or down. Even the simplest things change. Tears don't fall, fire doesn't rise, and slowly, your body loses the directions it trusted for its entire life. This video isn't here to make space feel frightening. It's here to help you understand it. So, take a deep breath. Gently let your mind relax. Allow the long day behind you to fade away. Tonight, we'll explore life aboard a spacecraft and the quiet changes space creates inside the human body. A spacesuit is not clothing. It doesn't exist to keep an astronaut warm, or comfortable, or recognizable. In space, a suit becomes something much more fundamental. It becomes an environment. Inside that suit, pressure is carefully maintained so that blood does not begin to boil in the low-pressure vacuum outside. Oxygen is continuously supplied, allowing the lungs to exchange gases normally, even when there is nothing at all to breathe beyond the visor. Carbon dioxide is actively removed, preventing it from slowly building up inside a sealed system. At the same time, heat is carefully regulated. Because space is not uniformly cold or hot, it is extreme in both directions. The helmet's visor is coated with a thin layer of gold, not for appearance, but to reflect intense sunlight that would otherwise damage the eyes. Every layer, every joint, and every connection exists for a reason. Without a suit, the human body cannot survive exposure to space. It's not dramatic, and it doesn't happen instantly, but the physics are unforgiving. At low pressure, fluids behave differently. Oxygen can no longer move effectively through the bloodstream, and the systems that quietly keep us alive on Earth begin to fail. A small tear in a suit does not cause an explosion. There is no violent rupture, but even a tiny leak allows pressure to escape rapidly, turning the situation into a true emergency if it is not addressed immediately. That is why every spacewalk is planned in detail. Suits are inspected repeatedly, movements are rehearsed, and nothing is left to improvisation. In space, survival does not depend on instinct or courage. It depends on engineering that works exactly as intended, every single time. A spacesuit is not what an astronaut wears. It is the smallest spacecraft ever built, designed to carry just one human being safely through an environment where biology cannot exist without constant support. And once gravity disappears, even the human body starts behaving differently. On Earth, gravity is always at work. Even when you're standing still, it gently presses down on the body, slowly compressing the spine throughout the day. Inside your back, soft discs sit between each vertebra, acting like natural shock absorbers. Under constant gravity, those discs remain slightly compressed, quietly supporting your weight without you ever noticing. In microgravity, that pressure disappears. Without gravity pulling downward, the discs in the spine begin to expand. The spaces between vertebrae widen just enough for the spine to lengthen. Over time, astronauts can grow taller by several centimeters, not because their bones change, but because the spine finally has room to relax. This change doesn't happen all at once, and it isn't painful at first. But many astronauts describe a feeling of tightness or pressure in the lower back as the body adjusts to its new shape. It's unfamiliar, not dangerous, simply a reminder that gravity has always been shaping us from the inside. When astronauts return to Earth, the process reverses. Gravity slowly compresses the spine again. Height returns to normal, and stiffness or back discomfort is common during those first days back under Earth's weight. Your inner ear, which quietly tells your brain which way is up and which way is down, no longer receives a clear signal. Muscles that have spent a lifetime working against gravity suddenly find nothing to push back on, and the body begins to behave as if the rules have changed because they have. In weightlessness, nothing falls. Objects don't drop. They stay exactly where they are left. The same is true for the human body. Blood and other fluids are no longer pulled toward the lower half of the body. They slowly shift upward, toward the chest and head. Faces appear slightly fuller. Legs become thinner. Not because anything is wrong, but because gravity is no longer sorting things the way it always has. Even the heart responds. On Earth, it works constantly to pump blood upward against gravity. In space, that effort is no longer necessary. The heart begins to work differently, adapting to a system with far less resistance. What surprises many people is how calm this process feels. Weightlessness is not violent. It doesn't force the body into distress. Instead, the body quietly starts letting go of habits it no longer needs. But that calm comes with a consequence. Without gravity providing constant feedback, the body slowly forgets how strong bones need to be and how much muscle is required to stand upright. Nothing breaks. The body simply begins to optimize for a new environment. Weightlessness doesn't attack the human body. It invites it to change. And understanding that difference between danger and adaptation is one of the most important lessons space has to offer. And over time, those changes become impossible to ignore. On Earth, gravity is always present. Even when you're resting, it constantly reminds the skeleton that it has a job to do. Every step you take, every moment you stand upright, sends a signal through the bones. That signal tells the body, strength is required here. And in response, the body maintains bone density, storing minerals to keep the skeleton strong enough to carry weight. In microgravity, that message disappears. Without a downward force pulling on the body, bones no longer experience regular mechanical stress. And the body responds in a way that is quiet, efficient, and completely logical. If a structure isn't being used, the body stops maintaining it. Calcium and other minerals begin to leave the bones and enter the bloodstream. Over time, the skeleton becomes less dense, not because it is failing, but because the body has decided that heavy, load-bearing bones are no longer necessary in this environment. This change doesn't cause pain. It doesn't announce itself. It happens slowly and silently. What makes it serious is the speed. Astronauts can lose around 1% of their bone mass per month in microgravity. That rate is far faster than the gradual bone loss associated with aging on Earth, which usually takes years to become noticeable. The excess calcium released into the bloodstream must then be filtered by the kidneys. This increases the risk of kidney stones and places additional strain on systems that were never designed for such conditions. For this reason, exercise in space is not optional. It isn't about fitness or appearance. It is a critical part of survival. Astronauts follow strict, daily exercise routines designed to recreate the forces gravity normally provides. Resistance machines and carefully planned movements help signal the body to hold onto bone mass, even when gravity itself is gone. Bone loss in space doesn't come from injury or impact. It comes from adaptation. The body isn't breaking down. It's responding exactly as it was designed, to adjusting to an environment where the rules have changed. And that is what makes space biology so serious. The danger isn't sudden or dramatic. It's the quiet consequences of the body learning the wrong lessons from a place it was never meant to stay. Without gravity, the human body becomes efficient in ways that are not always helpful. Muscles are designed to work against resistance. Bones are maintained by load. The heart adapts to how hard it needs to pump. Remove gravity, and the body quietly begins to let go. Muscle mass decreases. Strength fades. The cardiovascular system no longer needs to work as hard to circulate blood. None of this feels dramatic at first, but over time, the changes become serious. Without intervention, astronauts would return to Earth unable to stand, walk, or support their own weight properly. The body adapts exactly as biology intends, by conserving energy in an environment that no longer demands it. That's why exercise in space is not optional. Astronauts train for roughly 2 hours every day, not to improve performance, but to prevent loss. The goal isn't to get stronger. It's to stay the same. Treadmills are equipped with harnesses that pull the body downward, simulating the load of gravity. Resistance devices replace free weights, using vacuum and mechanical force instead of mass. Every movement is designed to send a clear signal to muscles and bones. You are still needed. Exercise becomes medicine. It protects bone density. It preserves muscle strength. It keeps the heart working at a level that will be necessary back on Earth. More than that, It provides structure. In an environment where days blur together and physical cues are limited, routine becomes grounding. Training sessions mark time. They restore a sense of effort and recovery that the body recognizes. Astronauts don't train to get stronger. They train to avoid losing what gravity normally protects. Space itself has no air, and without air, there is nothing to carry a smell. Yet astronauts often describe a distinct scent after returning from a spacewalk. When an EVA ends, suits and tools are brought back inside the station. As the airlock repressurizes and helmets come off, something unexpected appears. A smell, sharp, metallic, and strangely familiar. Astronauts have described it in different ways. Some say it resembles hot metal. Others compare it to burnt steak. Many notice a faint hint of ozone, similar to the air after a lightning storm. This scent doesn't come from space itself. It forms when high-energy particles interact with the surfaces of suits and equipment during a spacewalk. Outside the station, those particles trigger chemical reactions on exposed materials. But there is no air to carry the result. The smell only becomes noticeable once everything is brought back inside, when normal air allows those chemical byproducts to reach the human nose. In other words, space doesn't have a smell of its own. It leaves one behind. It's a subtle reminder that even in a vacuum, space still interacts with matter. It changes surfaces. It alters materials. And when astronauts return to a pressurized environment, those changes briefly announce themselves through one of our most instinctive senses. The smell doesn't exist out there. It follows you back inside. As sunlight reaches our atmosphere, it scatters gently, softened by the air, the dust, and the clouds. That filtering gives the sun its warm yellow color and smooths the transition between light and shade. In space, that layer is gone. There is no air to scatter light, no atmosphere to soften its intensity. Sunlight arrives exactly as it is, direct, unfiltered, and precise. As a result, the sun appears white instead of yellow. Its light is sharper, cleaner, and far more intense, and the shadows it creates are equally extreme. In space, there is no gradual fade from brightness to darkness. When something blocks the sun, it creates a hard, immediate shadow. One moment, you are fully illuminated. The next, you are in complete darkness. Temperature behaves the same way. Without air to distribute heat, objects don't warm up slowly. They heat rapidly in sunlight and cool just as quickly in shadow. There is no balance point, no comfortable middle ground. This is why everything in space must be carefully managed. Spacecraft surfaces are designed to reflect or absorb light in controlled ways. Solar panels are positioned precisely to handle constant exposure. And astronauts rely on layers of shielding to protect both equipment and their own bodies. The sun in space is not more powerful than it is on Earth. It simply follows simpler rules. There is nothing to soften it, nothing to moderate its effects. Only direct light and direct shadow, separated by a sharp boundary. This contrast is what gives space its striking beauty and its unforgiving nature. The environment doesn't adjust itself for comfort. It remains perfectly consistent, whether that consistency is helpful or harmful. There is no gentle shade in space, only light, darkness, and the systems we build to survive between them. And because nothing behaves normally up there, even eating has to be re-engineered. In microgravity, food behaves very differently. On Earth, we never think about where a crumb goes. Gravity quietly takes care of that. In space, there is no such help. Food doesn't fall, it floats. A loose crumb can drift into ventilation systems. A drop of liquid can separate into spheres and move wherever air currents carry it. And something as small as a piece of bread can become a real hazard if it reaches the lungs or delicate equipment. That's why eating in space has to be carefully redesigned. Astronauts don't eat regular bread. Bread creates crumbs. Instead, they use tortillas, which stay intact and predictable. Drinks come in sealed bags, pulled through straws designed to keep liquids under control. Seasonings are mixed directly into food or dissolved, so nothing escapes into the cabin. Every meal is engineered to behave. But food changes for another reason as well. The body itself works differently. In microgravity, fluids shift toward the upper body. Blood and other liquids move into the head and face, creating a sensation similar to constant nasal congestion. As a result, astronauts often experience a reduced sense of smell. And because smell plays a major role in taste, food can seem bland. To compensate, astronauts tend to prefer stronger flavors, spicy sauces, heavily seasoned meals, not for comfort, but simply to register taste at all. What's surprising is how quickly this becomes normal. Meals in space aren't about pleasure or presentation. They're about nutrition, safety, and consistency. Calories are carefully measured, textures are controlled, and every package is designed to open cleanly, close securely, and leave nothing behind. In space, food isn't just nourishment. It's part of the life support system. Every bite has to stay where it belongs. Every meal has to function inside an environment where even the smallest mistake can drift into something much larger. Space life isn't heroic in its daily moments. It's managed, planned, and quietly precise. And when eating finally ends and the lights begin to dim, another challenge appears, one that even engineers can't fully control. And when the day finally ends, sleep becomes its own kind of experiment. In space, there is no bed. Astronauts don't lie down at the end of the day. They slide into sleeping bags, lightly restrained, and attach themselves to a wall or a ceiling so they don't drift while they rest. Without gravity, the body doesn't need a mattress. It only needs a place to stay still. But the absence of a bed is the smallest difference. What's harder to adjust to is the absence of night. The International Space Station circles Earth roughly every 90 minutes. From orbit, astronauts can watch the sun rise and set about 16 times each day. Light and darkness alternate so quickly that the body can no longer rely on them as signals for rest. On Earth, sleep is guided quietly by the environment. Dimming light, cooling air, the slow arrival of night. In space, those cues don't exist. Instead, astronauts follow an artificial schedule. Lights are adjusted by mission control. Work periods and rest periods are carefully planned. The body is asked to sleep not because the world has grown dark, but because the clock says it's time. Sound becomes part of that adjustment. The station is never silent. Fans circulate air. Pumps move fluids. Life support systems operate continuously, creating a steady background hum. At first, the noise can be distracting. But over time, it becomes reassuring. Those sounds mean everything is working. They mean air is moving, water is flowing, the environment is stable. True silence, in space, can be unsettling. It may signal a system failure, something that needs attention immediately. Sleep, under these conditions, is not a habit, it's a task. Astronauts learn to create their own sense of night. They block out light, they anchor their bodies, they slow their breathing and allow the mind to follow. Even without darkness, even without gravity, the body still asks for rest, and when sleep finally comes, even something as simple as a tear behaves differently. Crying brings a small sense of release, not only emotionally, but physically. When astronauts cry in space, the moisture gathers into rounded droplets. The tears cling to the surface of the eye, spreading slowly across the skin instead of moving downward. They can blur vision, they can sting, and they don't provide the relief we usually expect. There is nothing poetic about it. This happens because surface tension becomes the dominant force. Instead of flowing away, it holds together quietly, refusing to leave. Astronauts can't wait for tears to dry or drift off. They have to wipe them away with a cloth, just like sweat, just like any other liquid that has nowhere to go on its own. What makes this moment striking isn't discomfort. It's the reminder. Even something as human and instinctive as crying still has to obey the laws of physics. Emotion doesn't disappear in space, but gravity does. Your feelings remain exactly the same. Your body reacts the same way. Only the environment changes how those reactions unfold. In space, nothing becomes dramatic. It simply becomes unfamiliar. And sometimes, the smallest changes are the ones that make the difference most clear, revealing how deeply gravity has shaped even our most basic responses. And outside the station, those same rules make survival far more fragile. A spacewalk is not a journey, it's work. When astronauts leave the station for an EVA, they are not stepping into an open frontier. They are entering an environment with no air, no pressure, and no natural protection of any kind. Outside the station, the suit becomes everything. It provides oxygen, it maintains pressure, it regulates temperature, and most importantly, it tells the body that life is still possible. Every movement during a spacewalk is deliberate. Nothing is rushed. Nothing is improvised. Hands move slowly, explained in advance, practiced countless times before ever reaching orbit. Tools are positioned carefully. Tasks are broken down into small, controlled actions, because even a minor mistake can be difficult to correct. The risks are real, but they are not dramatic. Loss of pressure is the most serious concern. So is losing orientation, not knowing which way to move when there is no up or down to guide you. Even small debris, traveling at orbital speed, can become dangerous if it strikes exposed surfaces. This is why preparation matters more than courage. Astronauts train for hundreds of hours before performing a single EVA. Much of that training takes place underwater, inside massive pools that simulate weightlessness. Every motion is rehearsed until it becomes automatic. One detail stands out. Astronauts are always connected to the station by a tether, not because they might fall, there is no down, but because without that connection, there would be no reference point to return to. Drifting doesn't feel fast. It doesn't feel dramatic. It simply continues. And without gravity, even your sense of direction begins to disappear. On Earth, orientation feels effortless. You don't think about which way is up or down. Your brain already knows. That sense comes largely from the inner ear. Tiny fluid-filled structures respond constantly to gravity, sending steady signals to the brain about position and movement. As long as gravity is present, the system works quietly in the background. In microgravity, that reference disappears. The inner ear no longer receives the familiar pull it expects. At the same time, the eyes continue to report motion and orientation based on what they see. The brain is suddenly faced with conflicting information. Vision says one thing. Balance sensors say nothing at all. For many astronauts, this mismatch leads to a temporary condition known as space motion sickness, dizziness, disorientation, nausea. It usually appears during the first few days in orbit, as the brain struggles to interpret signals it has never encountered before. This isn't weakness. It's biology responding honestly to a changed environment. What matters is what happens next. Instead of shutting down, the brain begins to adapt. It slowly reduces its reliance on the inner ear and places more weight on visual information and learned reference points inside the station. Walls, handrails, and familiar layouts become anchors for orientation. This process is an example of neuroplasticity, the brain's ability to reorganize itself in response to new conditions. Neural pathways adjust. Expectations shift. A new internal map begins to form. Over time, most astronauts regain a stable sense of orientation. They move confidently through the station. They rotate their bodies without confusion. Up and down are no longer required. The brain doesn't panic when gravity disappears. It learns. Disorientation in space isn't a failure of the human system. It's the first stage of recalibration. And this ability to rewrite internal rules is one of the quiet strengths that allows humans to function far beyond the environments they evolved in. The body adapts. The skeleton adapts. And so does the mind, reshaping reality just enough to make survival possible. But some things in space affect you, even when you're not moving at all. If you're still here with us, thank you. We truly appreciate you taking this time to explore the universe together. We hope this video has given you something valuable, not just information, but a clearer way of seeing how vast and fascinating the cosmos really is. We're always listening, always learning, and always trying to make these journeys deeper and more meaningful for you. If you'd like to support what we do, a simple like, a subscription, or sharing this video helps more than you might think. And without keeping you waiting any longer, let's continue our journey into what comes next. There is something surrounding every spacecraft in orbit. It has no sound, no color, no immediate sensation, and yet it is always there. Radiation in space isn't an event. It isn't an accident or a sudden burst. It is part of the environment itself. High above Earth's surface, the natural shields we depend on become thinner. The planet's magnetic field and atmosphere still offer protection, but far less than they do at ground level. As a result, astronauts are exposed to a steady stream of high-energy particles, arriving from the sun and from beyond the solar system. This exposure is significantly higher than what the human body experiences during normal life on Earth. Not enough to cause immediate illness, not enough to feel. That's what makes it different. Radiation doesn't announce itself. It doesn't cause pain. There is no warning signal when a particle passes through the body. Instead, its effects are subtle and cumulative. At the cellular level, radiation can damage DNA and interfere with normal cell function. Over time, this increases long-term health risks, something mission planners monitor carefully for every astronaut. One lesser-known effect involves vision. Some astronauts experience changes in eyesight during long stays in orbit, a condition known as spaceflight-associated neuroocular syndrome, or SANS. It's believed to be linked to a combination of fluid shifts and radiation exposure, affecting pressure around the brain and eyes. What matters most is that none of this feels dramatic in the moment. Radiation doesn't knock you down. It doesn't force immediate reactions. It exists quietly, shaping risk over time. Because of this, spacecraft are designed with radiation in mind from the beginning. Sensitive areas are shielded as much as possible. Time spent in higher exposure regions is carefully tracked. Missions are planned around solar activity to reduce unnecessary risk. Radiation in space is not treated as an emergency. It's treated as a constant, something to be understood, measured, managed. That perspective changes how danger is viewed. Radiation isn't an enemy waiting to strike. It's part of the background, an invisible condition of the environment. Just like vacuum or microgravity, fire feels predictable. A flame rises, heat moves upward, smoke follows. That expectation is built entirely on gravity. When gravity disappears, fire loses its sense of direction. Without an upward pull, hot gases no longer rise. There is no natural convection to stretch a flame into its familiar shape. Instead of flickering and leaning, fire behaves in a way that feels almost unnatural. In microgravity, flames form spheres. They burn slowly, evenly, and symmetrically, fed by oxygen diffusing gently from all directions. The color often shifts as well, softer, sometimes pale blue, not because the fire is weaker, but because the chemistry is more uniform. It's a striking sight. Quiet, controlled, almost beautiful. But that beauty is misleading. In space, smoke does not rise. It doesn't drift away from the source of combustion. It lingers. Without gravity to carry combustion byproducts upward, smoke and gases accumulate around the flame, surrounding it instead of escaping. This makes fire harder to detect, harder to manage, and potentially far more dangerous. The risk isn't explosive flames. It's slow, contained combustion in an enclosed environment. That's why fire safety is treated with exceptional seriousness aboard spacecraft. Materials are carefully selected to resist ignition. Electrical systems are monitored constantly, and strict protocols govern anything that could produce heat or sparks. Fire in space isn't more aggressive. It's more patient. It doesn't rush. It spreads. Because the environment doesn't help control fire, even a small flame has to be taken seriously. Metal usually behaves the way we expect. Surfaces touch, then separate. Parts move, rotate, and slide without sticking. That expectation depends on air. In everyday conditions, metal surfaces are never perfectly clean. A thin layer of oxygen forms almost instantly, creating a barrier that prevents direct contact at the atomic level. Remove the air, and that barrier disappears. In a vacuum, metal surfaces become exceptionally clean. When two pieces press together under the right conditions, their atoms can bond directly. No heat is required. No melting occurs. The result is a phenomenon known as cold welding. Two separate parts can quietly fuse into one. This isn't a malfunction. It's physics behaving exactly as it should in the absence of air. In space, this creates real engineering challenges. Bolts, joints, and moving mechanisms are carefully designed to avoid unintended contact. Protective coatings and lubricants are used to keep parts from bonding permanently. Cold welding doesn't happen everywhere. It requires specific conditions, but the risk is real enough that it's planned for in advance. The lesson is simple. Nothing breaks in space because it's fragile. It behaves differently because the environment has changed. When air disappears, even solid metal follows new rules. And just like machinery, the human body has its own quiet ways of responding to this unfamiliar environment. And the human body has its own way of reacting to this strange environment. Space often appears empty, quiet, still, but it isn't. Beyond the protective blanket of an atmosphere, even the smallest particles continue moving at extraordinary speed. There is nothing to slow them down, nothing to burn them away. Micrometeoroids are tiny fragments, often no larger than grains of sand. Yet they travel at orbital velocities, crossing space faster than bullets fired on Earth. When one of these particles strikes a spacecraft, the impact can create a brief flash of light, a sharp, momentary spark just outside the hull. From inside, it can look like a shooting star close enough to touch. The beauty is real, so is the risk. At these speeds, size matters far less than motion. Even a microscopic object carries enough energy to damage surfaces, puncture materials, or weaken structural layers over time. This is why spacecraft are built with multiple protective layers, not to stop impacts outright, but to absorb and disperse their energy. Each layer slows the particle down, spreads the force, and reduces the chance of penetration. It isn't about shielding against large objects. Those can be tracked and avoided. The real challenge comes from what can't be seen. Space isn't filled with threats waiting to strike. It's filled with motion. And motion, when unfiltered by atmosphere, becomes the defining danger. The lesson is subtle but important. Space isn't empty. It's active. Beauty and risk often share the same view, separated only by speed and distance. That's why creating life in space is far more difficult than it sounds. Growing a plant seems simple. Roots go down, leaves reach up. Those directions feel obvious because gravity has always been there to guide them. Remove gravity, and that guidance disappears. In microgravity, plant roots don't know which way to grow. They don't sense a downward pull. Instead of extending into soil, they spread outward, searching without direction. Water behaves just as strangely. Without gravity, it doesn't soak downward through soil. It forms floating pockets, clinging to surfaces or drifting away from where roots need it most. This makes growing plants in space far more complex than placing seeds in dirt. To solve this, astronauts use carefully controlled growth chambers. Plants are anchored using gels, fibers, or structured supports that provide physical guidance. Water is delivered as mist or held in place by capillary action, ensuring roots receive moisture without flooding. Under these conditions, plants can grow. Not quickly, not naturally, but they grow. Leaves form. Stems strengthen. Roots adapt to the signals they are given, even when those signals are artificial. The purpose goes far beyond food. Growing plants in space helps scientists study how life responds to unfamiliar environments. It tests whether biological systems can function when fundamental forces are removed. And it provides something less measurable, but just as important. Living plants change the atmosphere inside a spacecraft. They introduce color, movement, a reminder of home. For astronauts, tending to plants offers a quiet connection to Earth, a moment of routine that feels alive in an environment built entirely from metal and machinery. Plants don't grow naturally in space. They grow intentionally. Given the right understanding and support, life doesn't resist space. It adjusts to it slowly, carefully, and in ways that continue to surprise us. And the human body reacts just as strangely to life without gravity. Gravity does more than keep us on the ground. It quietly organizes the fluids inside the body. Most of your life, blood and other liquids are gently pulled downward. They collect more in the legs. The heart works against that pull, sending blood upward to the brain and eyes. When gravity disappears, that sorting system disappears with it. Fluids no longer settle in the lower body. They redistribute, drifting toward a more even balance. And in practice, that often means more fluid shifting upward into the chest, neck, and head. The change can be seen. Astronauts often develop a slightly puffy face. At the same time, their legs can look thinner. Not because anything is wrong, but because the body is simply rearranging where its fluids live. This shift usually isn't painful. It isn't dangerous in the immediate sense, but it can have effects that matter over time. When more fluid remains in the upper body, pressure inside the head can change. That pressure may affect the eyes, subtly altering vision during long stays in orbit. It's one of the factors connected to spaceflight-associated neuroocular syndrome, or SANS, a condition researchers continue to study closely. What makes this remarkable is how calm it feels. There is no alarm inside the body, no signal that says something is wrong, because in a way, nothing is wrong. The body is doing what it always does, trying to find balance in the environment it's given. It adjusts circulation. It changes how much fluid the kidneys remove. It adapts, step by step, to a new baseline that gravity would normally prevent. Fluid shift is one of the clearest reminders that space doesn't need to hurt the body to change it. It simply changes the rules, and the body quietly rewrites its behavior to match. Nothing is failing. Fluids are just moving. The immune system is built for patterns. It learns what normal feels like: regular sleep, familiar microbes, predictable stress levels, and it calibrates its defenses around that steady rhythm. Change the rhythm long enough, and the system begins to respond differently. Long-duration spaceflight introduces a quiet kind of pressure on the body, not a single dramatic threat, but a constant combination of stress, altered routines, and a background environment that is simply less forgiving than life on the ground. Over time, researchers have observed something surprising. Some astronauts experience reactivation of dormant viruses. Viruses the body normally keeps silent for years. They don't always cause obvious illness, but their return is a signal that the immune system is behaving differently. Part of this shift may be linked to stress hormones, including cortisol. When stress remains elevated, immune responses can change, sometimes becoming less effective in certain areas, or reacting in ways that are harder to predict. The key point is uncertainty. Not everyone experiences the same immune changes. There is no perfect way to forecast who will be affected and how strongly. Two astronauts can follow similar schedules, eat similar diets, and still respond differently. This is why space medicine focuses so heavily on monitoring rather than assumptions. Blood markers are tracked. Health is measured continuously. Small signals are treated seriously, not because space is actively causing disease, but because it can push the body outside its familiar balance. Space doesn't make you sick in a simple way. It shifts the conditions that keep you stable. Nothing new attacks the body. The body simply reacts differently to what it already carries and what it already knows. In deep space, that subtle difference matters, because survival is not just about strength. It's about maintaining stability when the environment stops supporting it. That's why every drop of water in space has to be carefully controlled. In space, water is not something you can replace. There are no rivers to draw from, no reserves waiting nearby. Everything the crew needs must already be inside the station or be reused. That reality changes how water is treated. On the International Space Station, water is part of a closed system. It's continuously collected, cleaned, and returned to use. Moisture from breath, sweat from the body, humidity pulled from the air, even wastewater. Nothing is discarded. The system is designed to capture these sources and process them through multiple stages of filtration and purification. Impurities are removed. Microorganisms are eliminated. The result is clean, safe water, suitable for drinking, cooking, and daily life. What makes this possible is efficiency. The station is able to recycle more than 90% of its water supply. That number isn't a goal, it's a requirement. Every drop that leaves the system would have to be replaced, and replacement isn't an option. This doesn't feel extreme to the astronauts living with it. It feels routine. Water moves through the station in a quiet loop. What was vapor becomes liquid. What was waste becomes resource. Nothing is wasted because nothing can be. There is no fear attached to this process, only awareness. The system works because it has to, and because it works, daily life remains calm and predictable. Over time, this creates a subtle shift in perspective. In space, water is never something you use up. It's something that changes form, passes through systems, and returns again and again. Technology turns limits into habits, constraints into stability. Space doesn't remove resources. It removes the permission to be careless with them. And once that permission is gone, every system becomes more deliberate, including the ones that keep humans alive. And on the moon, even dust becomes a serious problem. The moon looks quiet, smooth, almost gentle from a distance. Up close, it tells a very different story. Moon dust, known as regolith, is unlike anything found on Earth. There is no wind to round it, no rain to soften its edges. For billions of years, it has been shaped only by impacts and vacuum. The result is dust that never learned how to be smooth. Each grain is sharp and irregular, more like tiny shards than sand. Instead of rolling off surfaces, it clings. Instead of settling gently, it sticks to suits, tools, and skin. Apollo astronauts noticed the problem immediately. Moon dust scratched visors and cameras. It worked its way into seals and joints. It made moving parts grind and resist. Inside the spacecraft, it irritated eyes and lungs. Some astronauts even described its smell. A sharp, metallic scent, similar to spent gunpowder. Not because the dust is burning, but because of how it reacts after being exposed to air for the first time. What makes lunar dust troublesome isn't toxicity. It isn't poisonous. It's mechanical. The danger comes from abrasion, from friction, from particles that cut instead of cushion. Every movement on the lunar surface stirs it up. Every step carries it forward. And once it attaches, it doesn't let go easily. This is why future missions take lunar dust seriously. Seals must be redesigned. Materials must resist abrasion. Airlocks must limit how much dust follows astronauts back inside. The moon doesn't need harsh weather or extreme chemistry to cause problems. Its environment is difficult, in quieter ways. Moon dust is a reminder that every world has its own character, its own rules, its own kind of resistance. What looks harmless from orbit can become a daily challenge on the surface. The moon is not hostile, it's simply unfamiliar. And learning how to live there means learning to respect even the smallest details, especially the ones that refuse to be soft. And even the simplest daily routines have to change. Some tasks feel too ordinary to think about. Cutting hair is one of them. Without gravity, even this simple routine changes. Hair doesn't fall to the floor. It floats. Each trimmed strand drifts slowly, following air currents through the station. Left uncontrolled, those tiny fibers can be inhaled, settle into ventilation systems, or find their way into sensitive equipment. What feels harmless on Earth becomes a technical concern in orbit. That's why haircuts in space are carefully managed. Astronauts use electric clippers connected to small vacuum hoses. As hair is cut, it's immediately pulled away, captured before it can escape. The goal isn't appearance, it's safety. Loose hair behaves like any other floating particle. It can interfere with instruments. It can clog filters. And once it spreads, it's difficult to fully remove. This is what daily life in orbit teaches over time. Nothing is truly small when gravity is gone. Every object keeps moving until something stops it. A routine task becomes a controlled operation. Not because space is unforgiving, but because it is precise. In orbit, order doesn't happen naturally. It has to be designed, maintained, and repeated. Even something as familiar as a haircut becomes part of the system, quietly reminding the crew that, in space, awareness replaces habit. In orbit, there is no such thing as down. When an object slips from your hand, it doesn't fall. It keeps going. That moment, brief and quiet, is how space junk begins. A loose screw, a flake of paint, a forgotten tool. Each one becomes a free-moving object, locked into its own path around Earth. At orbital speeds, even something tiny carries enormous energy. Size doesn't matter nearly as much as velocity. A bolt no larger than a fingernail can strike like a bullet. Not because it's sharp, but because it's fast. Over time, these fragments accumulate. They circle the planet silently, crossing the paths of spacecraft and satellites again and again. Nothing pulls them out of the way. Nothing slows them down. That's why space operations are built around restraint. Every tool is tethered. Every movement is planned. Nothing is released casually. Not out of fear, but out of respect for how long consequences last in orbit. On Earth, mistakes tend to settle. In space, they persist. A dropped object doesn't disappear. It becomes part of the environment. This is what makes orbital space different from almost any other workplace. It remembers everything. The debris doesn't attack. It simply continues moving, following the same rules as everything else. Speed matters more than size. Motion matters more than intent. Space doesn't punish carelessness. It preserves it. And over time, those preserved moments build a system of risk that must be carefully managed, not with urgency, but with discipline. Because in orbit, nothing is ever truly lost. And nowhere does that reality become clearer than on Mars. Mars looks quiet from a distance, red, still, almost familiar. But the first thing it takes away is something the human body expects without question: air. Not because the planet is hostile, but because it was never built for breathing. The atmosphere on Mars is extraordinarily thin, roughly 1% of Earth's surface pressure. There is simply not enough air pressing back against the body to support life as we know it. And what little atmosphere exists is almost entirely carbon dioxide. There is nothing to inhale, and no pressure to keep oxygen inside the lungs. Here, breathing is not a reflex. It is a system. Every breath must be created, measured, contained. Without sufficient pressure, oxygen doesn't move into the bloodstream properly. The lungs cannot exchange gases the way they do on Earth. Even with oxygen present, the body cannot use it without pressure holding everything together. That's why survival on Mars begins with sealing the human body inside an artificial environment. A suit, a habitat, a controlled bubble of pressure and chemistry. Inside that bubble, air must be constantly circulated, filtered, monitored, and replaced. Carbon dioxide removed. Oxygen replenished. Not occasionally, continuously. On Mars, life support systems do not assist breathing. They are breathing. Water follows the same logic. There is water on Mars, but not in a form the body can use. Mostly locked away as ice beneath the surface. Frozen, inaccessible without effort. To drink, to grow food, even to create oxygen, that ice must be located, extracted, melted, purified, and reused. Nothing is free. Nothing flows naturally. Even the dust complicates survival. Martian dust is fine, dry, and electrically charged. It clings to everything: suits, seals, instruments. It works its way into joints and filters, slowly degrading the systems that keep air breathable. A single leak matters here. A compromised seal matters here. Because there is no surrounding atmosphere to buy time, no buffer, no margin. On Earth, air surrounds us in excess. On Mars, air must be defended. This is why human survival on the planet isn't defined by dramatic threats. Not storms, not cliffs, not sudden disasters. It's defined by continuity. Can pressure be maintained? Can oxygen levels remain stable? Can carbon dioxide stay low enough hour after hour, day after day? Every breath is an engineered event, and because there is no natural atmosphere to lean on, the systems can never rest. They cannot fail silently. They cannot drift. They must function perfectly not once, but always. This changes how humans would live on Mars. There is no outside without preparation, no casual step beyond the habitat, no forgetting. Even walking becomes a negotiated act between biology and machinery. Mars does not resist life. It simply ignores it. The planet follows its own physics: thin air, weak pressure, slow exchanges of heat. Human biology is the anomaly. That's why survival there feels less like exploration and more like an agreement. An agreement that says, if we bring everything ourselves, air, pressure, water, balance, the planet will allow us to stay. Break that agreement, and the body immediately feels the truth. The lungs don't struggle dramatically. They simply stop working. The brain doesn't panic. It fades. Mars doesn't punish mistakes. It doesn't need to. It just continues being Mars. This is what makes the planet so revealing. It strips survival down to fundamentals. Not courage, not strength. Atmosphere, pressure, systems that never stop. And once you understand that, you begin to see Mars clearly not as an enemy, but as a place that requires total honesty from the human body. Every breath must be made, every moment sustained, and even temperature behaves differently when there's no air to carry heat. Temperature in space is one of the most misunderstood things about space travel. People imagine it as a constant cold, a deep freeze. But space isn't cold in the way we think of cold, and it isn't warm in the way we think of warmth. What disappears first is the medium that normally carries heat for us: air. Without air, heat doesn't move through convection. There is no warm breeze, no gradual cooling, no gentle transfer. Instead, temperature becomes a matter of exposure. In direct sunlight, surfaces can heat up quickly because there is nothing to soften the radiation. No atmosphere to scatter light, no air to distribute energy evenly. Step into shadow, and the opposite happens. Heat leaves just as quickly, radiating away into space with nothing to slow the loss. That's why the difference between sun and shade can feel extreme. Not because space is trying to be harsh, but because it refuses to compromise. There is no warming up and no cooling down the way the body expects. You can be surrounded by emptiness and still overheat. You can be near bright sunlight and still lose heat rapidly once exposure changes. This is why thermal control becomes one of the quiet foundations of survival. Spacesuits and spacecraft aren't designed only to provide oxygen and pressure. They're designed to maintain a stable temperature in an environment that offers none. Layers of insulation slow the movement of heat. Special materials reflect radiation, and spacecraft use radiators' surfaces built to release excess heat deliberately, like a controlled exhaust. Heat must be managed the way water is managed: collected, moved, released at the right time. Because comfort isn't something space gives you, it's something you build. This changes the meaning of the word environment. In space, the environment doesn't surround you in a helpful way. It doesn't regulate anything for biology. It doesn't provide the soft background conditions that life depends on. So humans bring their own. A small, stable microclimate made of engineering pressure, air chemistry, humidity, temperature, all held inside a thin boundary that never stops working. Space isn't cold. It's indifferent. It doesn't attack with heat or cold. It simply offers physics with no cushion. And the moment you understand that, the logic of survival becomes clear. Staying alive in space is not about resisting extremes. It's about preventing extremes from reaching you at all. There is no gentle temperature in space, only controlled temperature inside what we build. Earth's orbit looks empty from a distance, a thin blue world wrapped in black. But it isn't empty at all. It's crowded with the leftovers of every decision humans have made beyond the atmosphere. Tiny flecks of paint, fragments of metal, bolts, shards, broken panels, entire satellites that no longer respond. They don't drift lazily. They move at orbital speed tens of thousands of kilometers per hour. At that velocity, size becomes irrelevant. A piece of debris smaller than a coin can strike with the energy of a high-speed projectile, not because it's heavy, but because motion carries power. This is the quiet danger of orbital debris. When objects collide, they don't disappear. They multiply. One impact becomes many fragments. Those fragments increase the chance of another impact, and that collision creates even more debris. A slow cascade, an invisible chain reaction. Nothing dramatic happens all at once. Orbit simply becomes harder to use. Paths that were once safe require constant monitoring. Spacecraft must track objects too small to see. Sometimes missions adjust their course for something no human will ever notice directly. This is how systems fail in space, not suddenly, but gradually. Because space remembers. Every object placed in orbit carries its momentum forward in time. There is no friction to erase it, no weather to wear it down. Time doesn't clean up after us, and time itself behaves differently up there. Not enough to feel, not enough to matter for daily life, but enough to measure. Clocks aboard orbiting stations tick at a slightly different rate than clocks on the ground. A tiny difference caused by speed and gravity. Just a few milliseconds each year. So small it never affects sleep, work, or conversation. So precise, it must be corrected for navigation systems to function properly. Time, like debris, keeps an account. Nothing dramatic, nothing visible, but exact. This combination, motion without friction, time without erasure, creates a kind of permanence. Actions don't vanish, they persist. A tool released accidentally doesn't fall. It becomes a long-term presence. A satellite abandoned doesn't rest. It keeps moving, crossing paths again and again. Space doesn't punish mistakes. It preserves them. This is why training matters. Before astronauts ever step outside a spacecraft, they rehearse for hundreds of hours. Every movement is planned. every tool tethered, every action measured. Not because one mistake is fatal, but because mistakes compound. And this is where physics quietly meets philosophy. In orbit, cause and effect are stretched across time. Separated by distance, delayed by motion, but never erased. Even time itself isn't absolute, yet it remains dependable. It bends slightly, just enough to remind us that the universe keeps records differently than we do. The lesson isn't that space is fragile. It's that systems are. When you remove friction, forgiveness disappears. Nothing fades naturally. Nothing resets. And so survival beyond Earth depends on thinking long-term, not emotionally, but mechanically. Every object launched, every fragment created, every second gained or lost, they all stay in the ledger. Space doesn't judge what we do there. It simply remembers. And sometimes, space leaves its mark directly inside the human body. There is a moment some astronauts describe that feels almost impossible to explain. They close their eyes. The cabin is dark. Nothing is moving. And yet they see light. Brief flashes. Thin streaks. Small sparks that appear without warning, then vanish. Not on a screen, not outside a window, but inside their own vision. This phenomenon has been reported since the earliest days of spaceflight. It doesn't require looking at anything. It often happens during rest, or just before sleep. The cause isn't imagination. These flashes are created when high-energy particles, cosmic rays, pass through the spacecraft and into the body. Some of them travel straight through the eye. Others interact with the optic nerve itself. For a fraction of a second, the nervous system reacts as if light were present. No pain, no damage felt. Just a quiet reminder. The universe reaches us even when we are perfectly still. This isn't dangerous in the moment. It doesn't interfere with vision or consciousness, but it reveals something subtle and profound. The human body cannot fully hide from space. Walls can block air. Suits can hold pressure. Radiation can be reduced but not erased. Some signals pass straight through. What makes this experience unsettling isn't fear. It's intimacy. Space isn't just something astronauts look at. It becomes something that touches perception itself. Light. Without light, a message delivered silently. For many, the flashes fade into routine. Another odd detail in a long mission, but they leave behind a lasting realization. There is no hard boundary between the universe and the human nervous system. Only layers, only probability, and that quiet interaction raises a much bigger question about the future of humanity. For most of human history, the environment shaped us quietly. Gravity pulled our bones downward. Day and night set our internal clocks. Radiation was filtered before it ever reached our cells. We adapted slowly, over thousands of generations, without noticing the changes as they happened. But leaving Earth interrupts that process. If humans begin living beyond this planet for long periods of time, the conditions that shaped our biology no longer apply in the same way. Gravity weakens. Radiation increases. Day and night lose their familiar rhythm. The body responds to these differences immediately. Muscles relax. Bones lose density. The cardiovascular system rewrites how it moves blood. So far, we know how to manage these changes for months, sometimes for years. What we don't know is what happens when those conditions last a lifetime, or longer. A child born in low gravity would never experience the constant downward pull that shaped every human before them. Their skeleton might grow differently. Their muscles might never need to support full body weight. Even their heart could develop around a reduced workload. Not broken, just different. Over generations, those differences could compound. This isn't speculation meant to alarm. It's an unanswered scientific question. We have no multi-generation data from space, no controlled experiments, no clear boundary between adaptation and transformation. What we do know is this: biology always responds to environment. Radiation doesn't need to be lethal to matter. Circadian shifts don't need to cause illness to leave an imprint. Small pressures, applied constantly, are enough to steer evolution. If humans remain off Earth long enough, space won't just be a location. It will become a biological influence. That raises a quieter, deeper question. If future humans are shaped by environments beyond Earth, will they still feel like us? Not in appearance, not in ability, but in identity. Adaptation always comes with trade-offs. Strength here, vulnerability there, efficiency gained, familiarity lost. Throughout history, Humans have accepted those trade-offs without hesitation. We adapted to cold climates, to high altitudes, to oceans and deserts. Space is simply the most extreme version of that pattern. The difference is permanence. On Earth, adaptation happens within a shared framework. Gravity remains. The sky remains. The planet remains recognizably home. In space, the framework itself changes. If humanity spreads outward, evolution may no longer be something that happens only in the distant past. It could become something we witness, slowly, quietly, across generations, not as a sudden leap, but as a gradual drift. And that drift doesn't mean loss, it means divergence. The environment writes itself into biology, whether we acknowledge it or not. The question is whether we are prepared to recognize ourselves in what comes next. Because space doesn't force transformation, it simply removes the conditions that once held us steady. And as humans have always done, we will respond. The only uncertainty is how far that response will carry us. Every satellite we send into space is built with a purpose. It observes, it communicates, it measures, and eventually, that purpose ends. When a satellite reaches the end of its mission, it doesn't fail in a dramatic way. There is no explosion, no collapse. It simply goes quiet. Its instruments stop responding, its signals fade, and what remains is a silent object still moving at orbital speed. Up there, motion doesn't require effort. With almost no atmospheric drag, objects don't slow down easily. They keep going, so a dead satellite doesn't fall. It doesn't disappear. It keeps circling Earth sometimes for decades. These inactive machines become something new, not tools, not failures. They become markers, fixed paths in space that trace where humanity has already been. Some satellites are guided back on purpose, lowered carefully into the atmosphere, where friction heats them until they burn away completely. A clean ending, but many others remain. Their orbits are too high, their fuel is gone, their systems are unresponsive. They stay, silent, predictable, still moving. Over time, they join a growing population of abandoned objects, each one a reminder that space keeps records far longer than Earth does. On the ground, abandoned machines rust. They erode. They vanish into the environment. In orbit, that process barely exists. Metal doesn't decay the same way. Motion doesn't fade quickly. Time stretches. A satellite launched decades ago can still pass overhead today, unseen but present, repeating the same path again and again. This is one of the quieter lessons of spaceflight. Nothing truly leaves orbit unless we make it leave. Space doesn't erase our activity. It preserves it, not out of judgment, not out of consequence, simply because the physics allow it. Each inactive satellite becomes a kind of ghost, not haunting, not dangerous by itself, but persistent. A trace of intention that outlives the people who designed it. And as humanity sends more machines upward, those traces accumulate, not as clutter, but as memory. Space becomes a record of what we chose to build, where we chose to place it, and whether we planned for what came after. Even when our machines stop working, they continue to move, still circling home. In space, the brain loses something it has relied on its entire life. There is no fixed horizon, no clear foreground or background, no single direction that feels more correct than another. For the human mind, this is unusual. The brain is not a passive observer. It is a prediction engine. Every second, it compares what it expects to see with what actually appears. On Earth, those expectations are reinforced constantly. Gravity pulls downward. Objects rest on surfaces. Distance behaves in familiar ways. In orbit, those patterns quietly disappear. At first, the brain struggles. Depth feels ambiguous. Near and far lose their usual meaning. Movement no longer provides the same cues. So the brain does what it always does when its predictions fail. It updates the model. Astronauts often report a subtle shift in perception after the initial adjustment period. Space no longer feels disorienting, it feels expansive. Not dramatic, not overwhelming, just open. With fewer visual anchors and fewer environmental demands, the brain reduces the constant background tension it normally maintains. There is less need to brace, less need to anticipate impact, obstacles, or sudden motion. Some astronauts describe a deep, unexpected calm. Their reactions slow. Their thoughts feel more spacious. Anxiety responses become quieter. This isn't because space is comforting. It's because the brain is no longer being stimulated in the same familiar ways. Without constant reference points, attention turns inward. The mind spends less energy correcting small mismatches between expectation and reality. Neuroscientists believe this shift reflects a change in sensory weighting. Visual input becomes less dominant. Internal signals, balance, body awareness, rhythm gain importance. The result isn't confusion, it's recalibration. Space doesn't overwhelm the mind. It simplifies the input. And in that simplicity, the brain adapts by letting go of assumptions it no longer needs. This is why some astronauts say space changes how they think, not emotionally, but structurally. The mind becomes less reactive, less tightly bound to immediate surroundings. It's a quiet transformation, not something you notice all at once, but something you feel in the absence of urgency. Space doesn't teach the brain new tricks. It removes old expectations. And when those expectations fade, perception becomes softer, slower, and more reflective. The world doesn't disappear. It becomes less demanding. In that state, awareness expands, not because space is vast, but because the mind no longer needs to defend itself against a familiar gravity. And nowhere is that sense of rarity clearer than with water. Water feels invisible when it is everywhere. It pours from taps. It falls from the sky. It waits quietly in pipes, bottles, and oceans. In space, that assumption disappears. Water becomes weight, mass, cost. Every liter must be launched, protected, stored, and recovered. Nothing can be wasted, because nothing is easily replaced. That single constraint changes everything. On board a spacecraft, water is no longer a background resource. It becomes a system tracked, filtered, reused, and cycled again and again. Breath moisture, sweat, condensation from the air, all of it returns, not because astronauts are being careful, but because survival demands it. Seen from orbit, this makes Earth look unusual. Against the blackness, the planet stands out not for its size, but for its color. That thin blue layer isn't decoration. It's circulation. Clouds move. Oceans breathe. Rivers connect land back to sea. Liquid water doesn't just support life. It allows stability. Elsewhere, water hides as ice, vapor, or trace minerals locked in stone. Here, it flows freely, cycling without permission, without effort. Space doesn't make water rare by removing it. It reveals how rare that freedom actually is. When astronauts talk about Earth, they often don't mention continents or borders. They mention blue, not as beauty, but as function. Because once water stops being ordinary, its meaning changes. It becomes time, energy, possibility. And when you return from a place where every drop is accounted for, it's impossible not to notice how much responsibility flows with abundance. Which leads to an unavoidable question about responsibility. When humans leave Earth, we don't travel light. We carry machines. We carry systems. And quietly, we carry habits formed over thousands of years. Space doesn't erase those things. It preserves them. Out there, nothing resets itself. There is no weather to wash mistakes away. No erosion to soften edges. No ecosystem waiting to absorb excess. Every action remains visible longer than we expect. A satellite placed in orbit stays there. A fragment released continues moving. A decision made once can echo for decades. That changes the meaning of responsibility. On Earth, consequences are often delayed, distributed, or hidden. In space, cause and effect stand much closer together. If something breaks, it stays broken. If something is abandoned, it keeps circling. If something is wasted, it cannot be replaced. So the question shifts. Not can we go farther, but how we choose to go. Exploration has always been framed as distance, new horizons, new worlds. But space suggests a different measure. Maturity. Because going beyond Earth doesn't free us from accountability. It concentrates it. Every design choice becomes ethical. Every shortcut becomes permanent. Every assumption is tested without mercy. What do we build for environments that will not forgive error? What do we leave behind when there is no away? These questions don't demand guilt. They ask for awareness. Space does not judge. It reflects. It shows us our strengths, precision, patience, ingenuity. And it reveals our weaknesses, excess, neglect, impatience. In that sense, space exploration isn't just about survival. It's about character. whether we can carry complexity without chaos, whether we can expand without scattering debris behind us, whether we can treat unfamiliar environments with restraint instead of dominance. The most important cargo we bring into space isn't fuel or air, it's intention. Because wherever humans go, we create systems. And systems shape futures long after individuals are gone. If we learn to move carefully in an environment that never forgets, that lesson doesn't stay in orbit. It comes home with us. Every journey outward quietly asks the same thing in return. Have we learned how to take care of what we touch? And eventually, every journey brings us back to the same place. When astronauts return to Earth, the first thing they notice is weight. Gravity pulls harder than memory expects. Legs feel uncertain. Balance has to be relearned, step by step. The body adjusts slowly, predictably. Muscle returns. Bones respond. The inner ear finds its reference again. But the deeper changes aren't physical. They're perceptual. Many astronauts describe the same quiet realization after landing. Air feels thick, heavy, in a comforting way. Breathing becomes something you notice, not because it's difficult, but because it's effortless. Water behaves again. It pours, it settles, it waits. Silence returns too, a different kind. Not the mechanical hum of life support systems, but pauses without alarms, fans, or schedules. Space doesn't teach astronauts something entirely new. It sharpens what was already there. Stability becomes visible only after it's gone. Abundance becomes obvious only after scarcity. Gravity becomes noticeable only after absence. That shift stays. Even years later, many say they move more carefully. They waste less. They pause longer before acting, not because space demanded it, but because it revealed how fragile normal really is. And that realization doesn't belong only to astronauts. You don't need to leave Earth to experience it. You can slow your breathing. You can notice the way water moves in a glass. You can feel the ground without questioning whether it will hold you. Perspective doesn't require distance, only attention. Space follows those who visit it, not as fear or awe, but as clarity. It returns with them, quietly embedded in habit and awareness. And for those listening now, resting at the end of a long day, the same lesson applies. Nothing needs to change for meaning to appear. Sometimes, all it takes is noticing what is already supporting you. And with that, the journey doesn't really end. Space doesn't ask to be conquered. It doesn't demand that we understand every equation, or remember every number, or hold every concept in mind. It continues anyway, moving, drifting, following rules that don't hurry and don't explain themselves. Out there, stars burn without witnesses, planets turn without concern, distances stretch far beyond intention. And here for this moment you are simply listening. You don't need to carry the facts with you. You don't need to organize them or make sense of them. They can fade. What matters is quieter than information. The slow rhythm of breath, the weight of the body resting where it is supported, the steady presence of gravity doing its quiet work. Space doesn't need your attention to exist. And you don't need to follow it any farther tonight. You've already traveled far enough. The universe remains vast, indifferent, and beautifully consistent. It will still be there tomorrow, and the night after that, and long after this moment passes. For now, there's nothing left to explore, nothing to solve, nothing to prepare for. Only the gentle awareness that you are exactly where you need to be. Grounded, safe. The journey continues not outward, but inward, into rest, into stillness, into the kind of quiet that doesn't need an ending. And for now, that's enough. Thank you for staying with us until this moment. If you're listening at the end of a long day, allow yourself to let go of whatever has been weighing on your mind. Settle into a comfortable place. Breathe slowly. Let your thoughts drift as the universe continues its quiet motion. There's nothing you need to do right now, nothing you need to solve. If you'd like, feel free to share your thoughts with us in the comments. We always enjoy hearing from you. Until next time, rest well and sleep peacefully.